Okay, so I think everybody can hear me. I hope everybody can hear me. I hope certainly everybody will be able to hear Kevin and Marie, who are going to be presenting today. So Kevin Devereaux and Marie Connolly. It's going to be 20 minutes. 20 minutes the presenters, and then about 10 minutes question and answers. That you please type into the chat box, and I'll try to stay on top of that. To Kevin, who I think Kevin is starting off, right? Yeah. If it looks like you're on time, I won't interrupt you, but if it doesn't look like it, I might butt in at some time. Okay. All right. Thank you very much, and for joining us, and take it off.
Thanks. Oh, and I'm getting to show my screen prompt, so I'm going to do this. Once again. How's that? Yeah.
So hang on.
Can you see the screen all right?
Yeah, that looks good, Kevin.
Great, thanks. Okay, so thanks everyone for coming here. Thanks to the organizers, Grant and Anna, for doing this, and thanks Fabian for chairing. So I'm going to talk about teamwork with an application that I think we should be all interested in, which is economics research. So the questions here are the best individual researchers the best co-authors? And I'll show you exactly the definitions I'm going to use for what are the best here. And how are academic researchers rewarded for value added to teamwork relative to how they're rewarded for solo work? So I want to define value added before going on. I think some people will be familiar with this, but I want to make sure it's clear. It's my contribution to a team compared to a replacement co-author, compared to somebody else. So it is relative to somebody else. Here's an example. If workers I and J are in a team and produce output Yij, and you compare them to team J and K, where one of the workers is the same, but another worker has changed. We have output measures from both of these two teams, and we'll say worker I's value added compared to worker K is the difference between these two output measures. So it could be the difference, it could be the ratio, it could be some other functions or something like this, but basically you're comparing the two output measures, holding worker J as the common factor, and using this as a basis to compare I and K. So what I do is estimate value added of co-authors in academic economics research. I compare this with their productivity on solo papers, and also I'm looking at earnings for a subset of the researchers. I'll talk about the data in a few minutes. And I want to look a little bit at the matching patterns among co-authors. These results are a bit more preliminary, and I don't want to hang my hat on them quite as much as the other ones. So what I find is that solo productivity and co-author value added, I mean, it's highly correlated, but on the other hand, it's not exactly the same. So the correlation is around 0.5. So there seems to be some common factor here, but there's a lot of variation between the two. So I would infer from this that some people are more productive at solo author, some people are more productive at co-author papers. Now, in terms of the payroll results, one standard deviation higher solo productivity is around $20K US higher earnings. This is only in the University of California system. I'm not using any payroll data for anywhere else right now. And actually the co-author value added, the value added to two authored papers, there's a bit more of a range here. This is not an exact confidence interval, but it ranges from, let's say, 10 to 20K. So really around the same range. I'll show you all the results. And there seems to be some matching patterns. These could be biased. We'll talk about maybe why, but we see positive assortative matching by the solo productivity and negative by the co-author value added. Okay, so I'm going to motivate this. I'm going to first tell you about the researcher data and results, and then the payroll results. So bullet point 2 here is big data. They're, a very big data set coming from ideasrepack.org. And the payroll data is actually going to be pretty small data. It's only a few hundred people who I've matched and who I'm observing payroll for, but this can be expanded in the future. So I don't want this to be navel gazing, economists studying economists. I think we can motivate it a bit more broadly. The share of workers in teams has risen over past decades in the UK, and it's been high in the US. It hasn't gone down, if anything. Now, these are two nationally representative surveys that give us the share of workers who are working mostly or usually in teams. And we see it's pretty high. It's above 50%. And if anything, it's been increasing. It hasn't been going down. Here's another side to looking at it. This is from firm surveys. And this is the share of firms with more than 20% of their workers in teams. And so this is high, and it's been going up since the 80s. These data sets are not nationally representative, but I think they pair well with the previous one. These are for larger firms in particular. And now I'm going to seg into the REPEC data. Here is share of papers that are co-authored in economics journals, and so it's a 0 if it's a single authored paper. It's a 1 if it's 2, 3, any number of authors, and the share of co-authored papers has been increasing. A lot of papers have documented this trend. Now, this goes back into the 40s, which I haven't seen before. I don't know if that's a novel finding or not particularly, but just it's been increasing, and it has been increasing also over the interval we see teamwork increasing in the general economy. So we should be interested in teamwork. And given that a lot of workers are working like this, we should be interested in how they're compensated for contributing to teamwork. Okay, so let me talk about the REPEC data set. I think a lot of you will be familiar with this. There are over 3,000 economics journals listed here. It ranks about 2,200 of these by impact factor. So I'd say about 2,200 of these are real journals. They have been cited at least once. They have a non-zero impact factor. So I'm going to use this as the main measure of quality or productivity of a paper. We can look at citation count also. This is comparable with Doctor et al. Forthcoming in Restat has about 1,600 journals from Econ Lit, and this is a very similar data set to what that paper is using. Now, here's how I scrape the data. I go to the journal page. So first I get the list of all the journals, and they have a journal page on REPEC. Now on the journal page, each of those contains a comprehensive list of published articles. So I want to emphasize comprehensive. For some journals, this goes back to the 19th century. I'm not going to end up using any data that old, but it is comprehensive. Now, once you get the comprehensive list of published articles, each of these lists the authors, citations, JEL codes, abstracts. That's pretty much it. Maybe one or two other tidbits. But the authors are indexed very nicely. Now there are registered authors. They have a unique REPEC ID code and a web page on REPEC themselves. They can be completely positively identified. Now the unregistered authors are consistently named across papers, and so the matching on of name to name on REPEC data is very, very clean. Okay, so I start with 1.9 million published papers. So first I'm going to discard the unranked journals. I'm going to today only look at papers with 1 or 2 co-authors. So this is over 80% of all papers over the whole data set. I want to look at bigger teams. Haven't done it yet. So I match authors by name across the papers, and this gives a network of co-authorships. And you can compare this network done by the people who are matched positively by REPEC ID, and I don't find any mistakes. So I think it's a very clean way to match people across papers. So now once you get to the co-authored papers, I have to restrict it to the largest connected set. I'll show you what that looks like in a minute. But the largest connected set is really almost 90% of all authors. So we're throwing away some authors who are who haven't co-authored with somebody who's co-authored with somebody who's co-authored with this biggest group here. I am throwing away those. Okay, so here are some summary statistics from the REPEC data. Team size, you can see when I cut the sample, it's 1 and 2. the year is going back to 1926. So in the largest connected component, somebody has worked with somebody who actually has a published paper back in 1926. Now I can get rid of the 20s, 40s, so on. I can cut this to the 70s. It's actually not going to change the estimates all too much. And I'll show you the sensitivity of that with a couple examples. Experience here, the first measure is just number of papers. So the drawback to this data set is there are limited observables. It's really just, it's mostly just the paper with some measure of quality, and then the authors who went into that. Experience in years is the number of years since your first published paper on the REPEC data site. Okay, now cites is citation count. This is another measure of productivity. Its distribution is quite a bit different from the rest of these variables here. I'm not sure if you can see the cursor, but I'm pointing to them. These simple impact factor, recursive discounted, H-index, and Euclidean. So those last 7 variables are the measures of output. So let's compare those. The impact factors all look pretty similar with, upwards of 0.8 correlation between them. The outlier here is citations. And so, of course, citations varies within a journal. None of the other productivity measures vary within a journal. So I'm going to give you results for citations, and for simple impact factor, show you that they're pretty similar. I'm not going to show any of the other impact factor results. Okay, so here's the decomposition. For solo authored papers, it's very simple. I'm taking just the average journal quality or the average citation count of the solo papers you've written, and that's your productivity at solo authored papers. So just averages, just these fixed effects. Now for the team production, I'm saying, okay, well, it's I and J on this team, and they have this team value added, which is called beta. And when they come together and work as a team, you sum these, and this is the output. So I can, they're multiplicative if you have the output as a log. I've done both. The results are robust to both of these. Now there is a little bit of a difference here from the worker firm two-way decomposition, which is that it's a non-partite matching setting. I'll show you what that looks like on this slide. So here are 2 example co-author data sets, just very stylized examples with 3 or 4 authors in each of them. So let's look at the triangle on the left-hand side first. There's author 1, 2, and 3. These are the nodes, and there are 3 papers, which are these edges between the authors. And here is what the data set looks like, 3 measures of output, and then estimate these parameters beta that are associated with the authors from the papers. Okay, so non-partite means that you can't label, let's say, author 1 as a worker and author 2 as a firm, because then what does that make author 3? Author 3 has worked with author 2, you'd think then, so you can't classify into 2 groups. So a lot of the tools that are used for these worker firm data sets are just actually not applicable here. Okay, now I want to illustrate the issue of singletons, and that is on the data set on the right-hand side. So I've just taken the triangle data set from the left and added worker 4, who has only worked with worker 1 and nobody else. And this adds an observation to the bottom, dummy variables here. Then we have an extra parameter, which is the value added for worker 4. This illustrates the incidental parameter problem. As you get more observations, if the observation contains a new author, then you also have to estimate a new parameter. Okay, so authors 1, 2, and 3 here are pretty well connected, and then author 4 is a singleton. So that's what I mean when I say that. Okay, so I'm gonna push right ahead to the results, and I'm gonna say, let's fit these decompositions to the actual data set. Okay, So here I'm giving you the distributions of the output measures on the left and the distributions of the productivity measures, alpha and beta, on the right. And the reason I put this sort of raw data along with these parameter estimates is that these alphas you can see are really just taking that distribution, in this case of simple impact factor, and averaging it by individual, but it looks pretty similar to the original distribution. This is, you know, something like an exponential distribution. When you decompose it and you put the betas and attribute them to one of the other two authors, then you're effectively subtracting some people's value added from the output of the paper to determine the other people's value added, and you get this sort of a smoother distribution that's that has tails on either side. Okay, so first thing I want to say is that this is a reasonable way to decompose the variation in the data. Whether or not you believe this production function with the betas summed together, these fit the variation well. So for the solo authored without singletons, has R squared of 0.57. Now, when you include singletons, you kind of cheat a bit if you're talking about explanatory power, because now I've added this beta 4 to the singleton, but it just perfectly explains this person's observation. So, you know, the explanatory power of the model doesn't rely on that. It's higher with it. It's got to be weakly higher with it, but that's not what it's based on. Now, the same thing is true for the two authored papers. Even has a better fit. Now, the thing about that is when you drop the singletons, you're actually dropping papers that contain other people who are more connected in the network. So if I were to drop author 4 here as a singleton, then I'm throwing away some of the information on author 1 who has worked with author 4, and it changes the estimate of author 1's value added. But it's really not sensitive to dropping these. And of the remaining authors, estimating it with or without singletons, the correlation is very high between the two. It's effectively the same. Okay. So here are scatter plots of the parameters some of these are team by team, some of these are within workers. So let me talk about first the top left corner. This is the alpha parameter, the solo productivity of the worker versus the value added of that same worker. And so this is to say, within a given researcher, are people who are productive per solo paper, are they high value added to two authored papers as well? And well, it's not 1 for 1, it's not 0, it's actually somewhere right in between, correlation around 0.5. Okay, now on the top right, we have solo productivity correlation across partners. This is taking from the co-author network who has worked with each other and just saying, not on the paper you work together on, but on your solo papers, are you, do you tend to work with people who are also high productivity? And it seems to be the case, a high correlation here as well. Now, the negative sort of matching results that I mentioned on one of the early slides, this is here talking about the beta parameters per partner. And this gives the joint distribution of beta I, beta J for all the IJ teams who work together, and there's a negative correlation here. Now this could be due to some downward bias, which we can talk about at the end if I get time. There are some techniques to correct for this in bipartite networks that don't work in non-partite networks, which is why I haven't done it here. Okay. So this says that high value added researchers tend to work with low value added researchers. And so I don't know if this this confirms your suspicion or what your prior might be on here. This holds even if I cut it by experience of partners, which I'm not showing exactly here. I'm showing the correlation between experience of partners, which is pretty weak. On the ends here, on the bottom right corner or the top left corner, this will be very experienced researchers working with somebody who's brand new. but that's not what is driving the negative correlation in value added across partners. Okay, so this is it for the researcher data. Now what I'm going to do next is match these productivity results to the University of California system payroll data. Okay, so this can be done for other states, other provinces. I chose California actually because they have some pretty nice records compared to the others. So one thing is that it's not censored at the bottom end of the distribution. It's not based on, let's say, the Ontario Sunshine List over 100K. I'm looking at everybody in the University of California system. So there are 10 campuses, a lot of students, a lot of academic staff, and the best thing about this payroll data is that it gives the sort of faculty group, which is business, economics, engineering. So everybody who I match their repack productivity to their payroll is going to be in business, economics, or engineering, and I'm going to match them by first and last name. So this is coming from different data sets. It's not as clean a matching as repack to repack. They're different records. Actually, even matching year to year in the University of California payroll system is a bit tricky, but they have the same first and last name, and if they're not in business or economics, they're an engineer. So that would be sort of the false positives that I could be getting here. And these come from this website called Transparent California, which you can download. It's freely available. Okay, so what I'm going to do, I take these estimates of alpha and beta productivities from the full sample, and then I'm going to use them to predict compensation in this payroll data. Now, something else that could be done is just to estimate productivity among the sample for whom I have the payroll. Now, this would be going from estimating productivity based on the whole universe of economics papers to just papers who were published by people who have been employed by the University of California system. So that's a very severe cut on the sample. That's really taken this sort of tiny bit of the sample and just estimating on there. And yet the correlation between the productivity estimates that come from either sample is very high. Oh, it's higher than I expected at 0.58. So you really severely cut the sample. You throw away all papers, all co-authored papers where one of the authors is not in the University of California system. So really you're throwing away a ton of stuff, and it's still a pretty stable estimate of the value added beta. So match using the first and last names, I get 606 matches. And this is 606 different people. Okay. Here are the productivity joint distribution results. The same things I showed you before, just repeated for this California only sample, and all the results hold up. They all look very similar. Okay. Okay, so let's get to the payroll results here. The first specification here is level earnings, and productivity is based on impact factor of the journal that the paper is published in. Okay, so by themselves, the alpha and beta productivity estimates predict about, let's say, around 20,000 higher US dollar salary per year, off a high base still. Now, putting them in together, they both have a positive prediction partial to each other. And in this, yeah, sorry, go ahead.
You might need to wrap up now if you can. Like,
okay. Okay. Sure thing. Yeah. Oh, sorry, I went over time. Okay, so these both have positive prediction partial to each other, and this also holds if you put in a number of publications fixed effect, since this is a productivity measure that just works, just happens per paper. So the rest of these slides are different specifications, and for the most part, yeah, these all look the same. You put it in logs, you put it in citation count productivities. So the conclusion here is some researchers are systematically more successful publishing collaborative research, 2-authored papers, compared to that same researcher publishing single-authored. But there is this common factor that predicts both of them. So there's something in common, but there's also this disjoint variation. And researchers are compensated more or less equally for their contribution to solo and 2-authored papers. So there doesn't seem to be a discount for 2-authored papers. And really these, these are looking about the same magnitude. Okay, so that's it. Thanks, Fabian.
Okay, so thank you very much for this presentation. I mean, what I really would like to know is what my contributions are, my scores are that you have in this data set. But besides that, we have a few questions that are coming in. So I'll start with Mikhail would like to know about whether you could identify complementarities between groups, such as experience or gender, by using the names and years since the first publication to identify these groups. Right?
Yeah. So there is some scope to do this. Now, REPEC lists the top 10% of women authors. And for everybody else, it doesn't have any gender information. So I do have to do it by name, but there's this subsample that I can check it on. And there's a computer scientist colleague of mine from Dublin has actually put me onto this thing called NameSOR. So I think it'll be a bit of a task. I think I can identify gender pretty reliably from what I've seen. I haven't done it yet.
And then what I would like to know is if you could briefly comment on essentially what you presented us were the fixed effects themselves, right?
Yeah.
Okay, so have you worked on, if you want to know what the distribution of these parameters is in the population, we're going to have to shrink these in some way. And specifically that negative correlation worries me a little bit on this. So could you comment on that?
Yeah, I think the negative correlation should worry you. So can you still see the slides here?
Yes.
Okay, so let me just go back to that. So yeah, here we go. So you know, I don't know if you can see the cursor or not, but looking at the team production function, beta I is really identified as the output minus beta j. So this creates this mechanical negative correlation between the value added of any two people who are observed to work together. So this problem is well understood in worker firm data sets. The correction technique relies on the network being bipartite. So I'm working on a solution for non-partite networks. I have a lead on it, but you know, this is it's something I haven't been able to pull off yet. Now, to get back to your point, if I were, say, to take the empirical based shrinkage estimate, something like this, then that would sort of weaken this mechanical negative correlation that's being pushed by this production function. The reason I don't have that ready yet is because I'm getting these estimates. There are tens of thousands of researchers here. In the cut sample, there's about 20,000 who I'm looking at. And so I'm not using ordinary least squares. I'm not inverting the matrix. I'm doing it with this conjugate gradient algorithm, which means I don't have the covariance matrix, which makes it hard to do that Bayesian shrinkage. So that is another problem I'm working on here, that the standard methods that have been done, you can't just apply them here. There has to be some change made to it. So these are two things I'm very cognizant of, but I'm still a work in progress.
Okay. So I'm going to read some more of the questions. They're coming in rapidly now, so it's getting harder for me to curate them before I read them out. I'm just going to go ahead here. So Francis Woolley asks, well, first he says it's super interesting work, but he also says citation levels vary across fields, right? So most brilliant economic historians will get fewer citations than people writing in finance, simply because some fields are bigger than others, right? So IIRC citation numbers are also increasing in time. So he's wondering to what extent this explains the positive correlation between authors' productivity measures. And then he also asked about the productivity salary relationship. So, and whether you have taken this into account, so these field differences and timing differences.
So I'm not doing anything to adjust for field or timing differences in citation count. So the main results, the ones that I went through on the regression table, so these are using the impact factor of the journal as the measure of productivity. So there's no sense in which these sort of headline results are influenced by citation count variation. This is the first productivity measure I looked at for that very reason, actually. So I agree with the concerns there. I think it is something that could be controlled for, but interestingly enough, even the magnitudes of these coefficient estimates look pretty similar using the citation count productivity measures. So these add up quite well with the journal impact factors. But I would need, that's the reason I put the journal impact factor as the main productivity measure. I think I can clean up this citations one a bit, but at a first pass, it looks pretty good, actually.
Right. Okay, so thank you for that. I think we're going to move on to Marie now. And thank you for your presentation. This was really very interesting.
Can you hear me?
Okay, Marie. Yes, we do.
All right. Can you see my slides?
Yes, we see them as well.
Great. Okay, so here we go. Now I can't see myself, but it's okay. All right. So thank you all for logging in and seeing this presentation. I'm going to talk today about parental education and the rising transmission of income between generations. This is joint work with my UQAM colleague Catherine Hack and Jean-William Laliberté, who's at the University of Calgary. And I wish we could have done this in person, but there you go. This is life in these times. Usual disclaimer, we're using StatsCan data, so this is our opinion, not the opinion of all the people on this list. So we're going to talk today about intergenerational transmission of income. You might have seen me present at CLEF in previous years on the topic. I've talked about a comparison between Canada and the US, as well as over time look at Canada. What we could see in this previous talk, looking at income mobility over time in Canada, is sort of what you see on the screen right now, which is an increasing rank-rank correlation over time. So you may be familiar, but I will repeat a little bit, go over what we mean by rank-rank correlation, because it's very central to this talk. So suppose you have two generations, the parents and the children, and you have a measure of income for the parents and a measure of income for the children. You can then compute the percentile rank of the parents in their generation and the percentile rank of the children in their own generation. And then if you try to explain the child's rank by the parent's rank, you get a slope coefficient, which we'll call beta here, which is the same as the correlation between the parental income rank and the child income rank, because both have the same mean. So on this graph, what you see is that over time, if you look at successive birth cohorts, precisely here we have Canadians born between 1963 and 1985, this rank-rank correlation has increased, which means that parental income rank explains more of the child income rank, which means that there's less mobility from one generation to the next, because your, so to speak, rank in your own income distribution is more explained or predetermined by where your parents were when you were growing up. And so what this is purely descriptive, and what we're trying to do in this paper is to look at the role of parental indication in the rising transmission of income in Canada. So what we want to say is, well, we want to find what can influence intergenerational income transmission. And the reason we want to do this is now that we've seen that that there's been a rise in the transmission of income across generations over time, we're trying to understand what happened, and we're also trying to understand what can possibly mitigate this relationship and move us towards more equal opportunities. And the first sort of candidate that we're looking at in this work is parental education. So we want to see if your parents are more educated, or if parental education rises generally, what will be the effects on this beta coefficient, this rank-rank correlation. In order to do that, we have to develop a new data linkage between administrative tax data and census data. The reason I'm saying this is the graph you just saw was purely based on income tax data, which is beautiful for its number of observations, very precise information, but does not have many socio-demographic variables attached to it. So we had to go and try to fetch this information from census data. What we then do, so what I'll spend the first part of the talk to do, is just to show you a few descriptive graphs and figures to show you how income mobility varies by maternal education level. And finally, what we're going to do is we're going to take 3 different approaches to try to get at the role of education. I guess what I should have said, well, I'll say it now. I should have said earlier, but I can say it now. The presentation that you're seeing today was originally meant to be all compacted into one paper, but as we're working on this, what we're going to do is we're pulling the 2 papers apart, and we're going to have one that is submitted to NBER. Is going to be a chapter in an NBER book looking at measurement of income. That's going to be the more descriptive side, and a few like the counterfactual exercise that you're going to see. And then another paper is going to tackle really the causal relationship through an IV method. So in this presentation, I'm going to try and very quickly summarize those different approaches. In the paper, they'll be separate. So we're going to use 3 different approaches, and there's going to be a bit more in the papers once they do come out. So our main findings are that parental education is associated with a boost in children income rank above and beyond what would be expected on the basis of parental income alone. So obviously there's a relationship here. The parent's education is going to have an influence on the parent's income, and then the parent's income has an influence on the child income through this rank-rank relationship. But what we'll see is that parental education in and of itself has an additional effect on children income rank. What we're also going to see is that the reduction in income mobility that we've seen in the first slide actually is particularly pronounced for families with low education. So when you split up the parents into education groups, what you'll see is that the slope increases particularly strongly for parents, in this case specifically mothers without a high school degree. And then the 2 bullet points 3 and 4 about the what our findings are in terms of the role of education. What we see is that the fraction increases in the fraction of mothers with a high school diploma. So when you go from no high school to high school, that reduces the transmission of income between generations, so it increases mobility. And we don't find the same thing for mothers with a bachelor degree. And in fact, what we find is that the supply of workers, of women with bachelor degrees, has increased, and the attached increase in the returns to education has made that as just further increased the rank-rank correlation. So has been boosting the increase in the income transmission. So the database that we use is the Intergenerational Income Database, which is administrative tax data that links over 6 million pairs of parents and their children. The new thing here is the linkage with the census. So we try to match each parent or the child to the census. In this case, we only care about a match with the parents, and specifically the mother. And so we look at, we have a match rate of over 68% with trying with the census from 1991 to 2016. The income measures that we use total income. For parents, we look at the average total parental income when the child is 15 to 19. For the child, we look at the child's average total income when the child is age 30 to 36. We've tried different specifications, and the results are robust, but this is what we use in the presentation. The rank-rank relationship, as mentioned before, is simply the beta that we're looking at is coming from a relation between the child income rank and the parental income rank. So first, descriptive statistics on maternal education in Canada. So this table is organized by child birth cohort in our data. So we have children born between 1963 and 1985. And for these children, what we see is that in 1963, 40% of the children's mother had no high school degree, 54% had a high school degree, and 6% had a bachelor degree. And if you go down the table to the last line, in 1985, the proportion of mothers with no high school credentials went down tremendously by 25 percentage points. The percentage with a high school degree went up by 16 percentage points, and with a bachelor degree went up by 9 percentage points. So these are large composition changes in the education distribution of the mothers. Next, we're going to look at the blue line here is the same line that I've shown you before, so the rising rank-rank relation over time. I'm just showing you this because this is the line for all children in the data set in the IID, but some of these children have mothers that are not born in Canada. For the IV instruments, we look at we use compulsory schooling laws that affected how much education a mother had gotten by province where the mother was growing up. And so what we do, we only look at children of Canadian-born mothers, so that's the green line on top. So what you see is the rank-rank correlation for children of Canadian-born mothers follows the same pattern, and slightly higher, but follows the same pattern. So now getting really to the education level. So this is the same rank-rank correlations that we saw before, but now where we split our sample into 3 depending on the level of education of the mothers. And the blue dots, so the series here on top, is for children whose mother had no high school degree, and the green for bachelor and red for high school degree. What you can see is that at the beginning of our observation period for children born in the early 60s, those rank-rank correlation were all sort of in the same ballpark around 0.2. At the end, the group that has seen a much higher increase in the correlation is the group of children whose mother had no high school degree. So all correlations have increased, but that is especially true for children whose mother had low education. Another descriptive presentation here, and what we do in this graph as well as in our first 2 methods, is just to simply compare children in the early part of our observation period and children in the later part of our observation period. So on the left here, you have children that are born in the early 60s, 1963 to 1966. We pull them together. We do the same for children at the end of our observation period, so children born from 1982 to 1986. The two plots are bin scatter plots, where each dot is on the x-axis, you have the percentile rank of the parents. And so each dot corresponds to a parental income rank. And on the y-axis, you have the mean child percentile rank, so for the child. And the series is decomposed into three. So we have the series for children whose mother has no high school degree, a high school degree, or a bachelor degree. And when you compare the two graphs side by side, what you see is that the increase in the slope for children without a high school degree, or for children whose mother doesn't have a high school degree, is especially pronounced at the bottom element of the income distribution. So this sort of increasing in the slope here for children whose mother doesn't have a high school degree. The other thing that's interesting is that the slopes, the series of dots, are sort of stacked upon one another, and what that means is that for a given income level, so if I take the 40th percentile, for example, here in 1963, 1966, the average parent at the 40th percentile that has no high school degree has a child who's roughly at the 45 percentile. But if your parents have a high school degree, then the child's rank increases to roughly the 50th. It's a bit more less precise for children whose parents have a bachelor degree in 62, 66, because there aren't very many of those parents. As you can see, the bulk of the distribution here for bachelor is in the top of the income distribution. But there's sort of a stacking here of the curves, which means that even at a given constant income level, your parents' education gives you a boost in your income rank. So what I'm going to do now is show you three different methods to look at the role of education. The first is going to be a counterfactual exercise. So what are we going to do? We're going to go back to the graph that we have here, and we're going to say, okay, what would the 1982-85 rank-rank relationship have looked like if we kept the same parental education distribution as 1963-66? And so if the education distribution has stayed the same, so no increase in the level of education overall, but keeping the location of the dots on the y-axis similar, what would the rank-rank relationship have looked like? That's going to give us a sort of simple or naive counterfactual for 1982-1985. The second method we're going to use is a method where we're going to compare unconditional to conditional rank-rank regressions. So unconditional is simply what I've shown you before. You look at, you run a regression of child income rank on parental income rank, and you get your beta coefficient. So we're going to look at that, and then we're going to compare it to a conditional regression where we look at we do the same thing, but we add a term that is the education level. So when we control for parental education level, how does the slope increase over time, and that's going to give us some insights into the role of education. The last thing that we're going to do, which is the IV part is still a work in progress. I'll get back to this. So we're gonna try to explain this beta coefficient, so the rank-rank relationship, by the percentage of mothers with a given education level. And here are the idea is that we have for each birth cohort and province of residence, we're gonna be able to measure a beta. And we're going to try to explain this beta by education levels. I'm going to show you OLS results, and the IV results is going to be the IV where we use compulsory schooling laws to instrument education levels. What I'm going to show you is done at the provincial level, and in future work we want to do it at going further down at the census division level to get more variation. Okay, counterfactual. So what we do here, I'll just go back to this graph here. If I look at this 1963, 1966, if I want to get an overall relationship without respect to education, what I get is these gray triangles, which is basically for each parental percentile rank. I sort of take a weighted average of the 3 dots that I had before, where the weights is a proportion of parents with no high school credential, or a bachelor degree. And so what I can see is that I have the earlier birth cohorts at an overall slope of 0.23, and for the later birth cohorts, I have an overall slope of 0.27. The counterfactual exercise that I want to do is say, okay, now I'm going to use the location of the dots on the y-axis that I had in the previous graph. But when I do my weighted average, instead of using the 82-85 weights, I'm going to use the 63-66 weights, as if the education distribution hadn't changed. And what you get is the series here with the little red pluses. And it's hard to see because they're close to one another. It's not that big of a difference, but you can see here that the dots, the pluses, are a little bit below the dots here in the lower part of the parental income distribution, and that the counterfactual slope is actually a little bit larger. So what this tells us is that if the education distribution had stayed the same as in 63, 66, which was lower education, you had more mothers without a high school degree. Now what you get is a higher slope. So the increase in education has actually helped decrease the slope, and so boost income mobility from one generation to the next. So that was our first pass at it. Our second pass is to look at the conditional versus unconditional slope. And so the conditional here are the round blue dots, and the conditional are the gray triangles. What you see if you compare 63, 66 to 82, 85 is that the unconditional slope has gone up from 0.229 to 0.269, an increase of 18%, whereas the conditional slope increases as well, but more so in absolute terms and in percentage. So it goes from 0.204 to 0.248. So what does that tell me? That tells me that once I control for education, the remaining parts of the rank-rank relationship has seen an even stronger increase than the unconditional rank-rank relationship. And so the increase in education helps mitigate this increasing in the slope. Our third pass at it is to look at the relationship between relative mobility and aggregate parental education. So what I have in mind here is I want to explain this beta PC, so the rank-rank mobility that we can compute per province of residence of the child and birth cohorts of the child. I can explain that by the education distribution for that group. So E bar is the percentage of mothers with a given education level. So I'm going to have mothers with a high school degree or a bachelor degree. And we can use cohort and province fixed effects. The first graph that I showed you is the visual representation of the OLS relationship. So here I'm interested in two education categories: having a high school diploma or having a bachelor degree, and the sort of reference group becomes having no high school credentials. And so what we can see is that places and birth cohorts where the fraction of mothers with a high school diploma is greater have a lower rank coefficient beta. And so this graph is showing, is using the bin scatter method by Cataneo et al. And so what you can see is that the OLS relationship between, if I try to explain the rank coefficient by fraction of mothers with a high school diploma, I get a negative relationship and a fairly large variation that gives me quite confidence that
Marie?
what I'm seeing is, yes?
You're also coming up to, well, kind of over the end already. So if you could wrap
Yes.
up as well, that would be great.
I am. So we see this negative relationship for a high school diploma, not so much for a bachelor degree. I don't have much time for the IV, but it sort of confirms what we saw earlier. So I'm going to conclude. I was almost there. Well, okay. So I guess from the only two things I want to say here is, one, from a policy standpoint, our results suggest that reducing high school dropout rates would promote equality of opportunity. We see the most action when you take people without a high school degree and now have a high school degree. That seems to be the driving force in the mitigation of the rising income inequality that we see. Income transmission. And what we still want to do is, especially for the IV parts, is to break it down at a finer geographical level. I haven't had time much to go into details here, but 20 minutes is really short, and I've already gone over time. So thank you, and looking forward to your questions.
Thank you, Marie. That was also very interesting. I have a question about the distribution of age at birth of your children is not the same across education or over time, but you measure the age of the parents when kids are 15 to 19. And we also know from Solon that this question about when you measure age of like income in the life cycle of parents and children matters quite a lot. So can you speak to that, whether you have done anything about this? Or?
We have for robustness checks and alternative specifications, one thing that we've done is we've looked at a different measuring the parental income at different times. And so one way to look is to look at it in terms relative to the age of the child, which is what I've presented you. But another way is to look at relative to the age of the parents. And so what we've also done is to compute the parental income measure when the parent is aged, I forget, I think it's 40 to 45 or some kind of age range like this. And our results are highly similar. So it doesn't make, that doesn't make much of a difference. One point that I need to mention here is that we don't look only at firstborns. And so the, while it's true that women have children later as time goes by, as the years go by on average, here we have all children. So for earlier cohorts, we have supposedly have somebody born in 63. Well, that person could have a mother that's actually fairly old because he might not be the firstborn of that mother. I don't know if that makes sense, okay. But yes.
So then I have a bunch of other questions. John Baker asks about whether these findings are quantitatively important. Right? He says that the rank correlations seem quite low. So maybe you can speak to the quantitative importance of your findings.
You mean the how much of parental education can mitigate the relationship, or just the size of the right?
I don't know what he means. You choose.
Right. Okay. Well, if I go back, hold on. Oh, I can't. Oh, okay. Here we go. Oh, I can't go back. Okay, here. Well, I'll show you here on the on this graph. This naive method shows that the slope has gone down by 0.01. So it's not. You're right that it's not a very large decrease, but if you try to get at factors that can sort of drive down this number that has been on the increase, then I think it's sort of anything that we can get is important. What our decomposition that I don't have time to show you shows is that we have we can sort of separate this effect into different effects, and the effect of completing high school is actually quite large compared to other parts of the of what we have, because we have effects that go in the other direction. For example, increasing returns to a college degree, private returns to a college degree, make our relationship go the other way. So you have a sort of bunch of factors that, when you put them all together, you get a fairly small decrease, but actually you have competing forces, and the force that is the most beneficial to reduce this relationship is completing a high school degree, which I guess isn't, we're not being radical when we try to promote high school graduation. So, trying to promote high school graduation is sort of gives us another sort of support because it can have impacts not just on the current generation that is getting their high school degree, but on the further generation. Sorry.
So I think I'm going to have one more question, and then we're going to wrap it up. And this one is about like whether mothers worked or not. This comes from Adam Lavecchia. He asked whether you did this exercise separately for children whose mothers worked and whose didn't, since conditional on family income, like whether you are in a single earner or two earner family, might put you in a different situation.
Yes. No, we haven't done that. We're only taking family income pooled, and we haven't separated where the income is coming from. So no, that's a good point. We could try to sort of do this. Thank you, Adam.
All right. Well, thank you very much to the two presenters, to Kevin and Marie, and to everybody who asked the question. Even if I didn't get to read them out, they will be passed on to the presenters and hopefully help them fine-tune their papers. And thank you very much for joining us.
Thank you.